Hey everyone, I'm David Room. Today I'm going to be doing some more work on the 3D mesh processing stuff. Something I always say long overdue, but something that truly is long overdue, and I'll get into that in a little bit. Um, I'm just having a nice day. I actually have the day off work because of Juneteenth, so I call this a lunch break stream, but nice day today to do all kinds of things. Let me just tweet out that I am live and then we'll get started. And I want to actually start by showing a couple things that I've been working on before we get into the programming. So, just 1 second here. All right. So, I haven't been live streaming a lot recently because I've been really busy with my day job. I'm actually getting ready to go on a second chunk of paternity leave. I had my third kid back in November of last year, but I get a couple of chunks of paternity leave that I can split up to use over a longer period of time. So, but I've been really busy with work, and then most of the time I've been working my project, I've been doing some 3D printing stuff, like actually 3D printing. So I've done a little bit of programming to prepare things. If you've been following these streams, you know that I'm doing 3D mesh processing to create these models of spaceships and stuff for my sci-fi world with a few different applications. Game programming, sort of high detail, more VFX style 3D art, which we're actually kind of working towards today, and then 3D printing. And I've worked through a number of iterations of things with the 3D modeling, but I'm really excited because I've actually got the high detail models being 3D printed. And I kind of figured out some settings to tweak so I can print almost everything in one piece. And the antennas were kind of the tricky part, but I added these sort of little blades to them, which I think look really good, and that sort of enables it to be 3D printed. And the only pieces here are the weapons, so they're sort of designed to have interchangeable weapons. I might add some other parts. Might add some other parts eventually too that can be swapped. So you can kind of mix, and the idea is you can kind of mix and match different weapons. But there's something about, and I didn't really get this when I started 3D printing, but there's something about sort of printing a high detail object all in one piece um, that just feels really solid and really good. And as models, these aren't really intended to be models. They're kind of intended to be more like sort of maybe display pieces or even toys. But like like this just feels really good in your hand. It looks quite good. I mean, there's some layer lines and some artifacts visible, but overall, I'm pretty pleased with the quality that I'm getting out of these. And these you can print in a few hours, so they're not super time consuming to print, and they're pretty rugged too. I think except for some of the little tiny parts. I'll show you. I've got one that I printed in black here. Some of the artifacts are maybe more visible on this one. I want to try something like a matte black, but still it's a really nice object just to hold. I mean, I'm biased because it's my design and it's fun to see it in real life, but um, so it's neat to be at this point, and it's fun to think about how future improvements that I make to my models, I can basically get this a 3D printed model of it for free now that I've kind of done the work, figured out some different different issues and ways to go about 3D printing and how to debug things. So, yeah. All right, so let's get into what we're going to work on today. I'm actually going to get a little bit of music started, and if anyone is watching and just let me know if the music is too loud relative to my voice. I'm still working out how to balance this stuff out, but okay. And we'll switch over to the desktop share. Okay, so What we're going to look at today is a new data structure for meshes. When I started this project, all of my experience, and that was like mainly from my job, was working with triangle meshes. And you know, at the end of the day, for games, really probably anything, like probably even 3D printing too, what you want is triangle meshes. So that's a mesh where, you know, you represent 3D objects as meshes, you have vertices, you have faces that connect the vertices. In a triangle mesh, all of the little individual polygons are triangles. You know, and there's some nice things to, you know, very nice aspects of triangle meshes. You always know you have triangles, you always know that you can calculate perfect face normals. The vertices can be represented as a you know, n by 3 homogeneous typed dimensioned array. But when you get into certain kinds of 3D modeling, specifically like modeling in Blender for higher detail, more VFX type stuff, you often want quads or even n-gons. So there's a lot of cases, even right now, where I'm like in Blender, I'm converting my meshes, my triangle meshes, to n-gon meshes and quad meshes to get better shading. And basically what I want to do today is I want to do some first steps towards investigating creating a polygon mesh type, so I can natively create meshes that have faces with an arbitrary number of vertices, and even like within the same mesh, different numbers of vertices per face. And you know, like everything else, it doesn't seem like this is going to be too hard. I'm sure there's going to be some interesting gotchas that we run into. But one encouraging thing is that, so I've been using this really great library called Polyscope as an interactive viewer. And I realized that Polyscope, you know, natively supports meshes with arbitrary polygons. So as we're building things and testing things, it should be easy using Polyscope to visualize what we're doing. So that's a big bonus and something that will make this a little easier. So let's dive right in and start implementing this, and I'll show you as we go kind of the way things are done currently, what will have to be done. I think a lot of the you know, mesh operations, like a lot of common things that you do with meshes really only operate on vertices, so they're going to be trivial to re-implement for polygon meshes. And then there's certain things like functions that I have for constructing meshes that should be straightforward to implement as like in a form for quad or polygon meshes. And basically I think it's going to be a situation where at least it seems like a handful of things will cover like almost all the cases, and then as long as I have easy methods to convert back and forth, adding this capability shouldn't really clutter up the code base too much, and it'll just be a nice tool to have in the toolbox. We probably won't get into like the native Blender integration today. We probably won't get into some of the algorithms. This is just going to be more basic stuff like visualizing basic mesh transformation stuff, but I think it should still be kind of interesting to go through this together and see how it works. So let's dive in. Let me just check a couple things quick, and then we'll get started. Okay. All right, nice. Doug Wise is here. He says he only has a few minutes of lunch overlap, but I'll come back and check out the rest of the night. Good to see another stream. Yeah, thanks for stopping in, Doug. Sorry I got started a little late here, but it's good to see you, and watch time later counts too as well. So I've been seeing a lot of activity on my YouTube channel lately, a lot of random views of old videos and stuff. So I've been anxious to stream again. I've just been so busy with my day job kind of getting ready for leave that I haven't had the time. But once I'm on leave, I'm hoping to stream pretty regularly again. We're actually going to be on vacation for a couple weeks of it, and I'm going to hopefully have a lot of time during that vacation to work on my project and stream too. So it's going to be not quite as nice of a streaming setup, but I think it'll still work. Okay, so let's dive into this. Okay, so the first thing we're going to do is we're going to sketch out the data types and modules and stuff. So I'm just going to close everything. And this is, so in my modeling library, which is where I have all of my data types and kind of lower level functions for modeling. This is my types. And mesh, I'm not going to rename mesh to triangle mesh. That would like touch every single file. So that's still going to be a triangle mesh, but we will we'll make a new thing. I think I'm going to call it a poly mesh. And for legacy reasons, mesh is a named tuple, because for the longest time it really was just a tuple without names of vertices and faces. It still is only vertices and faces. Unlike other libraries, I don't attach a bunch of other stuff. I like to keep things very pure and simple. Like what a mesh isn't a color, and you know, it doesn't have colors and UVs and stuff. A mesh is just a mesh. So we're going to use adders for the poly mesh instead of a named tuple, but it's basically going to be the same thing. So adders poly mesh frozen, because we like functional programming here, and this is we'll call it a polygon mesh. I need to make sure I know the exact terminology here. But I think polygon mesh is what I want. And we could, if we wanted to, at some point implement a quad mesh. The nice thing about a quad mesh would be that, you know, it would still have that nice consistently shaped face like vertex indices array, but I don't know a lot about algorithms for processing quad meshes, and to me, especially after seeing a lot of what I've seen on Twitter about using n-gons in Blender, I don't know how much advantages there are to like a pure quad mesh for really anything. The use cases that I have in mind, right away I would start using n-gons in. So I think we're gonna just jump right into a polygon mesh. So faces, and we'll make a poly faces type, because I'm still not sure what the right way to do this. I'm just gonna start with something dumb, which is gonna be basically a lists of ints. I don't think performance is like a super big concern for anything that we're doing here, so I'm not too worried about it. But there might be a way to do jagged arrays in NumPy or something like that. I'd have to look into it. I know there's jagged arrays in PyTorch or TensorFlow, but not sure about NumPy. But I know this will work, so we're gonna start here. So I swear I know the syntax of the tools that I'm using. Okay, so there's our polygon mesh, and then right away we're going to make a module for some of the different operations that we're going to want to do we're going to want to do on polygon meshes. Module, and I'm going to just call this polymesh. And we might split out like ops for this, but for now we're just gonna stick everything in one module, because where stuff ends up is not something that we want to spend a lot of time thinking about right away. Probably gonna have some conversion functions here. And let's just grab, actually, why don't we do a unit test right away? So test polymesh. And then let's take a look here. So I use a convention just of like to and from for conversion functions. So let's just add we want to go like to a mesh, and we want to go from a mesh. I don't think. Nice. Because you have like to and from tri-mesh. Yeah, I can always rename these to be something more specific if I add polymesh to like my general set of imports. Okay. And then before we get too far, we want to get our new Polyscope wrapper going, and to be able to handle this. And let's add a model type here that's going to be a union of, and this was kind of the intention all along, that this Polyscope wrapper could maybe do some other stuff. So this will be a union of mesh and polymesh. If we need to, we can backport some of these changes into our old Polyscope wrapper, but I think we probably won't bother doing that. Optional model. And I think we might not even have to touch anything, because if I understand how Polyscope works, basically when you add a mesh, the faces can either be an integer array or like a list of indices, or anything that's twice iterable, which yields integers. And this guy, you know, the latter option enables meshes where not all faces have the same degree. That's exactly what we want. So I don't know. We've got a default mesh here. This should probably be a constant. It's odd because this isn't really an empty mesh. That should be 3. Okay, whatever. Let's see here. And yeah, so I think all we want to do is okay, yeah, there's a couple things that we've got to handle here. Okay, so some of this logic will have to change for polymeshes. Interesting, that might be a function that we have to implement. Is an auto smooth function. But for now, let's just add an assertion here that mesh is a mesh instead of polymesh. So auto smoothing mesh objects. Okay, yeah, we've got some other conditions here. So that's fine. And what let's do is we'll just add a couple of different cases for printing. So we'll make sure that it's a mesh or polymesh here. And then if it's a mesh, then we'll do this. Otherwise, and then instead of the shape 0, we'll do when. Actually, here, this is actually simplify this. So is it class.name? Let's see here. So this a.class is this. And if I do, yeah, that's what I want. Okay. All right. So our viewer, I think, is good to go as far as being able to visualize these objects if we create them. So let's add a debug flag here. Oh, shucks. This is supposed to be here. Okay. Like it's true. So let's try this. Let's make a sphere. Radius 1 with 6 eggs and 6 rings. And let's just, we won't go through parts right now. We'll just use this wrapper directly. So we'll make a view object. Object or model is a sphere, and then just pd.view. I'm living in C++ land for work lately, so it's a little bit of a mode shift to write a lot of Python again. Okay, let's run this test. Shouldn't really do anything using the polymesh stuff left yet, but we'll see. So pytest-s. Oh, actually, I need to go in the modeling for this one. -s. Modeling. Oh, this should not be in the pointer folder. It should be up here. Modeling. Test. Okay, so there's our cube, just our normal cube. And when we look at the wireframe, this is just using the built-in wireframe functionality of Polymesh. It is obviously triangle mesh. Okay. Let's write something that we can convert polymesh or a trimesh or a triangle mesh to a polymesh with a with like a face epsilon. What's the word? Like an epsilon for the angle difference between faces for extracting facets. So yeah, let's do this. So polymesh So we'll do poly mesh. From mesh. Well, first of all, let's just we'll have two versions of this. So we'll just do a raw, straight conversion that goes to a poly mesh where everything's a triangle. That's like the trivial version. And then we'll do from mesh facets, and then this will force an angle. So we'll force like 1e to the minus 4 or something as a threshold or whatever. And we'll set these guys up so we're ready to go, and then implement the conversions. Okay. So here basically are our poly faces. We're just going to iterate over and construct lists of everything. Just do this actually on the same line, and then this will just be mesh.verts and our poly faces. Okay, now that was trivial, so let's just go on and do this more complicated one right away. So this, we're going to use a couple other functions. So sits and I think this guy uses, so this is using yeah, this is using the facet threshold. So what we got to do, oh nice, we can actually call this directly. Let's do that. Okay, nice. This is definitely what we want. So we're going to build a little wrapper here around the tri-mesh facet function. Now wait a second. Is this the one that doesn't include... yeah. The facets of the mesh that are single triangles. Yeah, so... there's this goofy thing where This guy doesn't get the complete set of facets. And, I don't know why that is. It just seems like obvious to me that it should include everything. But we'll experiment. Maybe this will be a good opportunity to see if we can figure out what's wrong with Trimesh. So, and let's just see here what the default tolerance setting is. Mesh.tall.facet threshold. Just call that facet thresh. And interesting. Ratio of radius to span. Okay, I'm not familiar with what that threshold means. I was confused about why it was 5,000. Whatever. We'll stick with this for now as a threshold since that's the underlying method that we're using. I'd like to write my own version of this later, not today. Okay, so this default threshold will be 5,000. And, okay, just for kicks and giggles, so we're going to convert to a tri-mesh, and then run the graph on it. I don't think I have a facets thing in my own graph wrapper, do I? School components, boundaries, no. And that's not in this library anyway. Okay, so our facets is going to be graph.facets mesh facet threshold equals facet thresh. And I think facets is supposed to be just a list of lists, right? Sequence of yeah, groups of face indices of parallel adjacent faces. Okay, so let's just see if this actually does include the triangles. So basically now we're just going to construct a polymesh where the verts are the mesh verts. You need to bother with that. It's just going to be verts yeah. Okay, look at that. PM. And this should be process equals false. Okay, hash dot words. Okay, now oops. That's strange. I sort this for some reason. Odd. Okay. What's up with that? ISort setting must be cooped up somehow. Okay. Now, what I'm expecting is that this isn't going to include the triangles. Ooh, interesting. Okay. Okay. So let's see here. So we've got these two work. Oh, this isn't quite right. This is the face indices. See, facets. Yeah. Okay, so this is the facets we need. This isn't. We need to convert these to yeah. We need to find the boundary of each of these. Oh, Skunk's Workshop is in the chat. He says, any chance we get a third Periapsis Christmas this year? You'll have to ask Katie about that. I think it's probably unlikely. But there might be other projects coming up. There might be some interesting stuff to keep an eye out for. And for sure, if that's something that you want, you should tell her about it. Because we certainly could do it again. What we saw is that like the interest like really fell off after the first one. I don't know if it was just like some of it was Amazon algorithm nonsense, but yeah. And we were also really busy last year because we just had a new baby. So I don't know. We'll see. We'll see what happens. Good to see you in the chat, though. Okay, so we need to find the boundary of each of those. And I think I've got something, facet boundaries. Yeah, so... Oh, yeah. Now, I feel like I came up with something that did this correctly. Facet boundaries. Did I not? Oh, good. Yeah. Oh, jeez. This is so horrible. Um... How did I get away without having... This is the classic, like, oh, this looks easy, but it's not going to be easy. Oh, so, yeah, Skunk's Workshop asks, is this the spaceship game? Would it be awesome to see you're still working on it? Oh, yeah. So I'm definitely still working on it. This is some tools that are more for the creating of assets for the game, right? And specifically, actually more working towards like higher detail assets. Like, I don't know if you remember when you were watching me doing some like high detail Blender rendering stuff. It's more towards that. So yeah, but definitely still working on it. Okay. Oh. Why is this? This makes me so angry that this is not ordered correctly. Did I fix this? Find boundaries. Okay. I think we might have to... Yeah, okay. So we're just gonna copy some stuff. We're gonna move some stuff into a graph module here. It's so stupid that I have to do this myself. And this is why you can't trust these libraries like TriMeshes. Like, they don't do obvious things. So there's a built-in capability to find the facet boundaries of a mesh, but it doesn't put the facet boundaries in the sensible order, which is the order that follows the triangulation. Like, there's an inherent order to those edges, and well, yeah, it's a little bit, let me think about this, putting myself on the spot. Yeah, there is sort of, yeah, there is an inherent order to those edges. There's an inherent order to the edges that's imposed by the triangulation. And the tri-mesh facet boundary finding stuff looks at it basically just looks at the edges without considering the order. Unless I'm using it wrong, but I don't think I am. The problem here, you can see it right here, is let's see here. Where is it? The problem is this there's a sorting that happens. Let's see here. Edges sorted. That, yeah. Basically, you can think of each triangle edge as actually having, you know, like when you have two triangles coming together, you can think of there being like two edges. You know, one that goes one way and one goes the other way. And this just doesn't account for that. So we're gonna do it in an awkward roundabout way just to get this going, and then we're gonna go from there. Man, makes me mad. Okay. So we're gonna start copying some graph utilities from our experimental module into the main module. This crap probably needs to go. So this guy and this guy is what we want. The problem and the tricky thing about this kind of stuff is that there's all these like variants and variations on these algorithms, and the tricky thing is if you don't find the right one, then sometimes sort is not working. Oh, I bet I need to, yeah, that's why. Okay, that's a project for another time. Yeah, because here what we're doing is we're not sorting these edges, right? And here we're discarding edges that have the corresponding reverse. So we're looking at the boundary. And we're using a directed graph, simple cycles, yeah. So we're gonna do kind of a goofy roundabout thing here. Don't want this. Yeah, and this is the thing, is I can do this conversion myself. In fact, I think there's a in the ship viewer, I do actually use something like this myself. So we might be able to pull out some of this stuff to use. Yeah. Yeah. So that'll be a little project for me, not during a stream, is using some of this stuff that I wrote up to implement my own version of some of this stuff that works properly. Okay. So, what we want now is we want to take a subset of the mesh for each facet, create a mesh, then find the boundary of that, and then create the facet out of that. So, oh no! This is also something that is in my experimental. Let's see here, facets. Subset mesh faces. This. This is so simple. This needs to be in. This just needs to be in util. Kind of a stupid patch, but okay, so that's going to go in there. Now we can do our util.subset faces facet. Now we can find the boundary of the facet mesh. Oh, but we've got to map that back to the this isn't quite what I want. I think about this. Okay. Okay. Yeah. This, actually, I don't need that. Yeah. So let's see here. We want to map. We want to get indices into the original set of vertices. So we just want to construct a mesh by keeping the original vertices but the faces basically being a subset of the faces that is the facet, because the facet here is the indices of the faces that belong to that facet. Now, when we find the boundaries, boundaries is going to be graph.find boundaries of that facet mesh. The indices are going to correspond back to the original. This should be of length 1. So PF, then we can just append boundary 0. And then there's our PF. And this just wants a list, so we got to convert it back to a list. And we can get rid of that. Is this right? I think it is. Because these are indices into the original vertices. We're passing the original vertices through. And then, yeah. So, Skunk's Workshop asks, do you also create particles through code, for instance, when firing laser cannons? My game doesn't have a lot of particle effects in it. The things like bullets and laser beams are meshes. So yeah, they're created with code. I can actually just show you quick here if I haven't broken anything. So yeah, like when I shoot, those little bullets are like they're little meshes. Let's see if I can find where that is. Yeah, so it's just a surface of revolution, which is a old, outdated method, but it's a surface of revolution of a little shape like this that makes that cone shape. Actually, I can just show you what it looks like. Oops. Now I've done it. This is what I get here. Yeah, see, and this is, yeah, see, this method is kind of what I'm doing, but it's this like finding the boundary of each subset. But here we're losing the original vertex information. Yeah, so it just looks like this, and then we scale it. We scale it. We scale it along the y-axis to like stretch it out for different size missiles or bullets or whatever. And then the laser cannons are just the lasers are just cylinders. So yeah, when you fire a laser, it's just basically a long cylinder, and then it has a glowing material on it. Hope that answers your question. Okay. Yeah, I think this is right. So I think we should see what we get. I think the question is here is let's switch gears and do something more calming. Do some LA sunset. I'm glad I started this now because this ended up being somewhat more intense than I was expecting it was going to be. Okay, it ran. That was good. Yeah, I think we're missing the triangle. Why does it do that? Why doesn't it include triangles? That is so weird. But look, we've got our quads. All right. Such... Why? Why doesn't that include triangles? Okay. So basically what we have to do here is we just have to find... Yeah. Let's just rewrite this logic. So basically we have to find all of the remaining individual triangles that are not included in this. Okay, so yeah, so the triangles is basically, you know, all of the individual, this is going to be faces, actually write this over here too. So this is all of the, and I'm trying to get away from shape 0. So basically, the set of all indices, the set of all triangle indices, minus the set of indices that are in this, right? And then I don't know why you wouldn't want this. Why would you not want facets to be a list of it's bizarre. Okay, and let's just do the conversion here as well. So we want to convert everything here to a list. And then we don't need the actually we do need the list here. Facets. Okay. it's just mind-boggling. Okay. Yes, there we go. Now, supposedly, it's saying that this has 36 faces. Should we count them? So we got 6 here, 6 here, and then we have 1, 2, 3, 4 rings that each have 6. So that's 6 plus 6 plus 6 times 4 is 36. So we did it. Okay. Wow. That was a rather intense little session. But basically we have a functioning polymesh type now, and we have a nice example of it working. So this definitely needs refactoring, because there's going to be a lot more sort of general places where I'm going to want this kind of functionality. It's good to actually move this functionality into my modeling library, because this is widely used. It's a very generic thing to want correctly oriented edges of a boundary. Let's just, as long as we're, I think this is probably a good stopping point, because, you know, the next step is going to be getting into constructing polymeshes, and that might be a good thing to do later. This is kind of like an initial hurdle that I wasn't expecting, but I think we got over. And it was good to review what some of the shortcomings in these current approaches are, and think about writing it myself. Like, really what I want is I want my own facet finding function that does what it should, which is actually include triangle faces. But yeah, let's see. Yeah, we went a good long time. We've had a lot of viewers. I think we should, maybe about an hour. Actually, it's only been an hour and 15 minutes. I think I'll keep going, and as long as people are watching, we'll keep going and try to do a little bit more construction of these things. So, actually, another piece of low-hanging fruit would be converting back to a mesh. And this might be another thing that, you know, I have all the pieces, but converting back to a mesh is going to require to move pieces from my experimental module into the main modeling module, which is good to do. So we'll do a trivial conversion. Actually, is retriangulated? Yeah. XP. Yeah, this is good. This is good. Some good kind of. This is a good forcing function for some good refactoring in my modules, so in my project. So trivial conversion from a polymesh back to triangle mesh. Let's see here. And I think a second. Because something that this does is it loses the information. Yeah, this is trivial, but it's not trivial in the sense that I already have all of the pieces implemented. What we want to do is we want to do this without losing the original vertices. So like we want to preserve the original vertex sees order, and that is also something that we want to do here, right? Because we're seeing mesh.verts, we're seeing the vertices of the original mesh pass all the way through. A lot of my functions for doing this stuff don't do that preservation, so I'm just trying to think. So let's see, triangulate. This might have a lot of extra logic that I don't want to bring into here. Functions of the quads. Just gotta think about this for a second here. This actually might be a little bit complicated to do right now because there's a bunch of like indexing stuff that I don't really want to mess with. Let's actually pivot back over to creation, because see that I have this actually okay. Okay. I take that back. We can do this. I have this other function that does kind of fancier retriangulation that it sort of like handles some nice cases, and I don't think that we care about a lot of this stuff here. So I think we can actually just use this and yeah, we can use this. We can do some transformations, we can do some cheap triangulation, and I think there's an easy mapping back. So yeah, let's try to do that. Okay. Okay, so we're gonna set up a similar thing here. So to facets type. Okay, so we're gonna be doing something similar here. Oh, actually, yeah, didn't need to do that. Okay, because we already have the poly faces, right? So polymesh is a polymesh, and we're going to return normal mesh. Okay, so for face and poly faces, so each of these faces is a list of indices. Okay, so Nick asks, so what am I looking at here? Obviously not C#, haha. Yeah, so I'm doing some 3D mesh processing programming in Python using NumPy, built-in Python data structures, and the TriMesh library, and NetworkX for graph stuff, and Polyscope for visualization. Yeah, and the end goal here is 3D modeling the programs. So just as an example of it, I have this 3D printed spaceship model that's printed from a model that I created using code. Yeah, Python code created this model. So yeah. Okay. Let's yeah, okay, so each of these is a list of indices. Now we want to pull out the corresponding verts, base verts. Well, actually, wait a second. We still need to find the boundary. Yeah, we still need to do this. Oh no, yeah, geez, it's interesting thinking through this because I'm not used to working with polygon meshes. This is not just the verts; it's already a boundary. So it's already a boundary. It's already a boundary, and it's already ordered in a correct way. So now we just need to pull out the verts. Boundary verts. Is polymesh.verts boundary. Okay. Now, this is the thing. So we don't know yeah, what we don't know here is we don't know the orientation that we want to do the triangulation in. I'm going to just assume that we can find that there's, yeah, we'll just take 3, you know, we're going to assert that there is at least 3, and then we'll sort of build a triangle that will find a normal up here. So try normal as of just the first 3, right? Yep. So and then we will do this and triangulate? I don't think so. So we gotta, now we have to reorient that loop to be lie in a 2D plane. I'm just reviewing how I normally do this. Oh geez, yeah, okay. And yeah, so that's gonna give us, this guy gives us the rotation that makes that normal go to Z, unit Z. Oh, jeez. Ah, but it's nice because this is already a nice oriented, ordered boundary. So boundary verts. Ops. Rotate verts, boundary verts. By rote. Okay, and then we're going to verts 2D is just going to take X and Y. And then we'll triangulate it. And then we have to just map back into our original boundary list. So faces is going to be triangulate dot triangulate poly, and then we have to map back to parentheses, which because we subsetted down here. So I think it's just faces equals boundary. Faces. And then actually, oh, that's not faces. This is vert indices. Right. Oh no, that's faces. Yeah, but faces are lists of... Ah, jeez. Okay. I'm missing a layer here. So, faces equals boundary Y for Y, X for X in faces. Right. And then we just have to, we're not building polyfaces, we're building faces all, and we just have to extend that faces all dot extend faces turn this into a array. Somehow NumPy isn't imported yet. Maybe it is, it's just not moved up to the top or whatever. Okay, and then this is all. And then we just gotta return our mesh, which is gonna have our original verts and our new faces. Polymesh first, verts. And this should be a yeah. All right, I think that's it. Should we see? So this isn't really guaranteed to give us a nice triangulation. But it's going to preserve the original vertices because we're passing that straight through. Okay. Let's try this. So. And let's just call these A, B, C, and D for clarity. Polymesh.from or to mesh. Oh, sorry, I haven't been paying attention to the chat. So, oh, Skunk's Workshop asks, you printed it. When did this happen? Yeah, so I've been kind of working on 3D printing since the beginning of the year, and just in the past couple weeks I got, I think, a pretty good method down for like high detail 3D prints. Nick asks, are materials coded too? Yeah, so I don't have... I'm not sure if I can bring an example up right now, but all of the high detail Blender stuff I do uses procedural materials like shaders. A couple of them I have some like external bitmaps that I'm bringing in, but it's like mostly procedural. And the game that I'm making uses very simple sort of not flat shaded, but it doesn't use textures, so all the materials are just, you know, shaders with very very well defined properties. And yeah, so the whole pipeline kind of works well with this programmatic modeling approach that I'm taking. Hope that answers your question, Nick. Okay. So we're going to convert sphere C back to a mesh. Does this look right? Okay, let's see if it works. Oops. Well, it ran. Okay, so here's our original sphere. We have the trivial conversion to a poly mesh that should have identical original triangulation as the original. And all these should have the same number of verts. There's the polymesh version with quads and triangles. And then our retriangulated version. Does this have maybe a little bit different? Yeah, it has a little bit different triangulation than the original, which is to be expected, right? There isn't really a... there isn't a convention that necessarily implies that one triangulation is better. So, and not only do these all have the same number of vertices, they should, the vertices should be in the same order. I don't have a really good way to visualize that or check that, but I think we can kind of see that, right? We're passing the original verts through here, here, and every one of these functions we're passing the original vertices through. So that's another really cool thing about this that I wasn't quite picturing in my head, is that when you do this conversion, if you have indices into the vertices, they stay. It's just a different triangulation. So awesome. Well, I think we're gonna call it good here for today. We've gone for a good long lunch coding stream, and yeah, a good hour and a half, and we got kind of the basics and some kind of obvious stuff that I was like, oh, that should be easy, that required a little bit more refactoring and rearranging than I was expecting. So I think it's a good place to stop. Thanks to everybody who hung out. It's always fun to hang out while I'm doing this, and if you're interested in what you saw, I have a ton of other live streams and videos on my channel of work on this project going back a few years. So yeah, thanks again, especially to everybody who's new. I hope you had a good lunch break, and I hope that you're encouraged to work on your own creative projects as well. So hope to see you again. Bye.